All right, happy Valentine's Day, everybody. So, as my Valentine's Day gift to you, this is I know I say this all the time, but I've had this video pending for a long time, one I've wanted to do, and this is about something you can do when you are SEM imaging, at least on the FEI/ThermoFisher microscopes, to help you if you're experiencing some charging issues. Now, it doesn't work, again, depends on how bad the charging is, but this can help. Again, assuming, it's not crazy bad. Um, but there's a technique you can employ when you are SEM imaging if you're experiencing charging to help alleviate this, and it's called scan interlacing. Okay, so right now, um, these are my conditions, of course, 2 kilovolts and 100 picoamps. So right now I am doing a traditional scan approach. Okay, so this is my dwell time. This is my pixel resolution. I'm scanning left to right, top to bottom. Okay, so I'm scanning one line going down, or scanning one row going down to the next row, left to right from top to bottom. Okay, and obviously I can increase my dwell time, and then you can actually see as it goes through more clearly, right, as this is happening, okay? And so um, this is obviously the traditional approach. So now I can acquire images, and so we're seeing actually right now, we're seeing some of this charging here. So this, here, let me come up here, mag in on this. Okay, so we're seeing the effect of some of this charging here, right? And there's also some down here and here. So this is, I don't know what this is exactly, but it's charging, okay? So um, we can from here, right? If we wanted to take an image, we could take a single pass or we could do frame integration. In either case though, right, it's doing um, for whether it's single pass or frame integration, for each frame it's doing top to bottom or left to right, top to bottom, right, as it's scanning. Okay, so just to give you an idea, now let me mag in on here because it's going to be a little easier to see, I think. Yes, so here we've got this stuff. You can see very clearly that this is charging, and so I'm going to do a single pass at 20 microseconds so you can see the result. And you can see very obviously that we're getting scan excursions here. So this is a photonic crystal or photonic device. It's based on indium phosphide. This is like a gold solder and it's bonded to this what's called a submount, which is very insulating. I believe it's aluminum nitride. And so we can see very clearly that, yes, we have some charging issues here using a single pass approach. Let me go ahead here and save this. Call it today's date. Okay, so we'll do, because we're going to compare the images here. 5,000. Single pass. Okay, so now let's look at what happens if we do frame integration approach instead. Okay, so we come back up here. Now, if we integrate the frames, one way to kind of tell you what it's going to look like when you do this is to do an average. And so you can see we can adjust the contrast up a little bit more here. I mean, we're still obviously getting charging. I'm not really clipping the detector here. Let me reduce this down to 8. Yes, okay. So let me I have a setting here for integrating 20 frames. Again, each frame it's doing the traditional left, right, top to bottom passing. So we're still seeing the same problem with the charging. Oops, I don't think I put that in the right place. Okay, so okay, let me really quickly find that. Yeah, there it is. Okay, so just looking at this, that's the frame integration, that's the single pass. So it looks like just by doing frame integration, we've improved the situation somewhat. But to be sure, we could improve this more, okay? So what can we do? We can employ a technique called scan interlacing, okay? So again, right, it's going row by row as it scans. If we perform scan interlacing, so the interlacing is defined in terms of blocks of rows, okay? So let's say that we do a scan interlacing of 2. So basically, it's going to divide the image into blocks of 2 rows, and it's going to scan the first row in each block, and then it's going to go back and scan the second row in each block. Okay, so that's what scan interlacing is. So you can do this, right? Come to your scan menu, go down to scan interlacing, and you see you have these options from 2 to 8. Okay, now the stipulation with this for this to work is that your total frame time has to be less than or equal to 300 milliseconds. Okay, so you can't do this for an arbitrary dwell time, as we're going to see. Okay, so I know at this pixel resolution, if I exceed 300, and I'll show you this. So let me turn on, sorry, scan interlacing. We'll do 8 here. Now you can see just in the live picture already, a lot of that went away. Okay, but see if I increase this, right, the interlacing goes away because you can actually see right up here it says SI for scan interlacing. Okay, if I increase the pixel resolution, it also goes away. Okay, if I drop it down to the next setting, I can use it though. Okay, so again, your total time for the frame has to be less than or equal to 300 milliseconds. Okay, so this is the highest I can make the dwell time at this next level of pixel resolution. Okay, so let me go back to this guy and let me bump this up. Okay, so now probably the easiest way to see, I'm going to zoom in here, and now watch what happens when I blank the beam. Oops, maybe I zoomed in too much. Okay, let me see here. Okay, hopefully you can see it there. You can see how it separates out into the blocks, right, as I blank and unblank the beam, okay? So you can see, right, the blocks of 8 rows as it's doing this, okay? And again, if I change this to, say, 2, you can see that those blocks, hopefully you're seeing that, those get finer, kind of depends on when I, start and stop this. So it's a little arbitrary, but hopefully you can kind of see that, okay? If I go up one more, can I see this? Yeah, so you can kind of see it here. It's a little more obvious, I think, here, even though the digital zoom is less, okay? So, in principle, I believe the more you interlace, the better your reduction in charging is, but this is an approach to reduce the effect of the charging. And so we can actually see this right now. Okay, so if I change, this is the same setup, same condition, except I turned off the scan interlacing here. Okay, for the okay, I turned off the scan interlacing for this acquisition. Okay, but you can already see some of the charging is starting to come through here. So you can watch what happens. This is the same preset here. Again, this is a scan interlacing of 8, and it goes away. Okay. So now, as far as acquiring a final picture with this, since we can't exceed 300 milliseconds for the frame, we obviously can't do really, well, we could do single pass, right? So this is single pass, okay, with the scan interlacing, and that doesn't look very good, right? So what we have to do here is we have to frame integrate, okay? So I have this S5 preset set for, okay, lowest pixel resolution, 300 nanosecond dwell time, scan interlacing of 8, and it's going to integrate 64 frames, okay? So now if we want to see, it can be tricky to adjust your contrast and brightness because you have a lot of shot noise here, especially if your current is low. So if I come here to average, or right here, okay, this gives me a better idea of what my final histogram is going to look like, okay? So now if I acquire this, you can see that the effect of the charging has been reduced pretty significantly. Okay, so I'm going to do scan interlace 8. Okay, now unfortunately I had to drop to the lower pixel resolution when I did this. Okay, and again, right, you can see if I make the dwell time too long, the interlacing turns off. Okay, so now one thing that when you're doing frame integration, you do have the option to correct the drift when you're doing this. The problem though with this is depending on your current, you may not have enough signal to noise in your image for the drift correction to work very well. So in my experience, you need sufficiently high signal to noise for this to work, and you need uniqueness in the picture, right? So at this low of a current, so we can try doing drift correction here, and we can see how this works. Okay, and I guess that's actually not too bad. I've seen this actually fail though sometimes. So when you're doing scan interlacing and you're doing integration, sometimes it can actually be beneficial to not turn on drift correction, again, assuming there isn't any drift. Now, there really isn't any movement happening here, so we're really not seeing a detriment as a result of that. If there actually was a movement, we would have a problem, okay? So I have another setting here to show you. So this is the higher pixel resolution, and this is 50 nanoseconds here. Okay, so you can see, right, my signal to noise is getting less, right, because I have 50 nanoseconds per pixel. Again, I can set up an average here, and we can see how this looks. So this is set to drift correct, and this is going to integrate 128 frames. And we can see that this isn't working like, well, it's not working terribly well. Yeah, so, I think, let me change this here. Yeah, I'll add the drift core 01, that's fine. Let me turn this off and see here. Yeah, so I think this actually, in this case, this is working better without the drift correction. at least in the case where the sample is, legitimately not moving. I mean, we'll have to do a comparison here. Okay, so there are trade-offs to doing this, right? Obviously, so you have to do frame integration when you're acquiring. Obviously, that's one frame at 50 nanoseconds a pixel, and that certainly doesn't look good. Obviously, like if we had a higher current, we would have better signal to noise per pixel, right? We're down here at a lower current, so so it can help you in that regard if you're using a higher current, certainly. So now if we actually, I have this paused. Let's take a look at this. Okay, so that's single pass. Okay, that's frame integrated. That's with scan interlacing of 8. Okay, you'll notice the pixel resolution is less. That's with the drift correction. So there really isn't much of a change here between the image with and without the drift correction with the scan interlacing on, which is good, I suppose, right? Because it means the sample's not drifting and it means it's aligning the frames well. You can see here when we bump up to the next highest pixel resolution, though, that this doesn't work quite as well, okay? So it actually looks a little bit better. I don't know if you can see that, but it actually looks a little bit better with the drift correction off than with the drift correction on. So that's drift correction on. This is 50 nanoseconds with the scan interlace. Oh, I put 9 there. That should have been 8. My bad. That's with the scan interlace of 8 with the drift correction on, and that's with the scan interlace of 8 with the drift correction off. Okay, so sometimes, right, I know it's counterintuitive, but sometimes turning the drift correction off can actually be beneficial. Okay, and actually, yes, I did put 8 here. Whoops. So I don't know why it did that. Okay, so let's look at this in order here again. All right, so that's single pass, 20 microseconds, and that's at the higher pixel resolution. That's frame integration, 20 passes, 1 microsecond. That's the scan interlace 8 at the reduced pixel resolution with no drift correction. That's the same thing, but with drift correction, again, really not much difference here. And then this is the next highest pixel resolution, but with drift correction and then without drift correction. So this actually looks better at the lower pixel resolution when you're doing the scan interlacing. So as sometimes somebody once famously said, right, sometimes less is more. And this happens to be an instance of that. So anyways, just wanted to share that with you today. That's my Valentine's Day gift to you is scan interlacing. So again, I have a preset here for it. And actually to do an apples to apples comparison, let me do this guy here. So this is without the scan interlacing. Let me turn on the average here. Okay. Okay. So this is frame integration. Whoops. Microseconds. So now if we're doing an apples to apples comparison here, we have that guy and we have that guy. Okay, so this is frame integration, 300 nanoseconds per pixel with no scan interlacing, and that's with the scan interlacing. So hopefully you can see the difference there. We don't have the charging quite as bad. So just in general, though, as we reduce the dwell time, that seems to help, right, with the charging. Okay, but adding in the scan interlacing on top of that is an added boost to the charge reduction or the charging reduction. So anyways, I was looking for a good example to actually, record this, and I finally came across one. So I wanted to, document this while I had a chance to do so. So anyways, happy Valentine's Day, everyone, and good luck with your microscopy.